Okay. So here's my example. So this is the kind of problem that you will see on your homework 4. It's going to be kind of a challenging type of problem to do. What I'm going to do is just go through it, and then afterwards I'll kind of codify the problem-solving strategy that I took into more discrete recipes so that you can apply to other problems. I just don't want to do it right at the moment because it's kind of will seem very abstract if we haven't done anything yet. So here's my problem. I have a ceiling and I have a wall. This is outside my shop. I'm starting a new shop. Okay? I'm going to hang a nice sign for my shop. And just to be clever and bring in more customers, I'm going to attach my sign to the wall like this with one rope, and then to the ceiling diagonally with this other rope. So I have 2 ropes, which I'll label 1 and 2. Rope 1 is horizontal to the best of my ability, but rope 2 is going to be diagonal, and that is going to be at an angle theta, and theta is going to be 30 degrees. And also my sign has a mass of 1 kilogram. And so, obviously I don't want my ropes to break because then it'll fall on my customers' heads and they won't be coming in my store anymore. So I want to make sure that the tensions in both ropes don't exceed whatever is the manufacturer reporting maximum tension. Okay? So I want to calculate how much tension is in each rope when the sign is hung like this. I want to just know the sizes of those. So when I write the tension without the vector hat again, that just means size up. Okay? So let's go through this. In this problem, I'm not looking for the acceleration of my mass. I hope that it is what? 0. I hope that the sign stays with no acceleration. What I'm hoping is that the 2 tensions in the ropes can make sure that the acceleration stays 0. So let's figure it out. Well, I have the force of gravity is certainly pulling down on my sign. If that were the only force, it would accelerate down at 9.8 meters per second squared. But luckily I have 2 other forces, both from the tension. This rope pulls, so notice it points away, right? Ropes always pull, never push. And then this rope pulls, so points like that. So notice that I've made sure both tension forces point along the rope away from the object. Alright, so that's 3 forces going off in all sorts of directions. So what I might want to do here is break it up into something that is more digestible. So I'm going to choose my x and y axes like this. And the reason I choose that is not because that's what I always choose. In fact, we're going to start choosing some really weird stuff. So if you look, for instance, at that vector practice worksheet that I posted, it has some really weird diagonal and flipped around axes, and you might wonder, am I just messing with you when I ask you to do those? Well, no, we'll have plenty of cause for some weird axes. The reason I choose these particular axes is not because that's what I always choose. It's because that means that these 2 forces I don't have to do SOHCAHTOA with, right? This is already completely just minus x, and this is already completely minus y. So I don't need to do any SOHCAHTOA. It means that I can minimize how much of that stuff I have to do. There's only one force, T2, which is diagonal relative to my axis that I've chosen. So for that, I can break that up into components, T2x and T2y. Alright? So what I want to do is I want to basically cordon off the problem into 2 bins, an x bin and a y bin. Just like I was talking about before. And I want to add up all my x components over here. And after that battle has been fought, and we see what the x components, they might reinforce, they might kill each other. Anything that's left over will be the net force in the x direction, so will cause the x acceleration. Same thing over here. I tally up, whoops, f1y, f2y, dot, dot, dot. I see what all those add up to, and if there's anything left over, which is the net force, it'll cause an acceleration. So that's what my situation is. Okay? I want to tally up what's going on in this problem and then make it more digestible by looking at the x and y axes independently. Okay? And in order to do that, well, I see, of course, that this one, let's go ahead and bounce this one off to the side. Let me take those x components and y components and quickly get what they are. Hopefully you can see that both of these components are positive, and hypotenuse times the appropriate trig function. So there I have it. I've taken the diagonal force of that rope and thought of it as a horizontal and vertical pull independently. This is usually a good stage to make the problem more digestible by putting in what's called a free body diagram. So a free body diagram. What a free body diagram is you basically free the object of interest from the rest of the fancy drawing and just draw it all by itself, hence the term free body. And what I like to do is on this free body diagram, do not allow diagonal forces. I want to think of everything as a tug of war on the two coordinate axes. So let's write it down. For instance, I have that part of T2 pulls to the side, and part of it pulls up. T2 sine of theta. So I'm digesting that diagonal force as a right pull and an up pull. Notice the notation that I'm using. What is in the parentheses is the size, and then the plus and minus is out front. Okay? So what's in the parentheses is the size, and then plus and minus is out front, depending on whether it's a positive or negative component. Let's do the other two forces. The force of gravity, it has a size of mg, so I'll put that in parentheses. Remember, g itself is not negative, so I need the negative out here because that's a negative y component. So again, in the parentheses, size. Outside, plus or minus, depending on axis choice. Finally, I do that with T1. It's got a size of T1. The direction is negative, negative x. So you see what I have is a push-pull that I can think of as a vertical fight, right? So I have two forces which are opposing each other vertically, and I have two forces which are opposing each other horizontally. A good free body diagram is worth its weight in gold because it pretty much tells you what's going to happen. Here's what's going to happen. If we want that thing to stay at rest, then gravity is going to have to be canceled off by this component, right? And if we don't want it to move one side or the other, then this is going to have to cancel this. That's basically a visual representation of what we're just about to write down with the equations. So let's do it. In the x direction, we have one competitor in the positive direction and one competitor in the negative direction. And what's the x acceleration again? 0. We don't want it to go anywhere. So we get those two components kill each other, which of course just simply means, solving here, that the two sizes are equal. We pretty much could have gotten that from the free body diagram, right? If these two are going to kill each other, then this is going to have to equal this, right? Let's do the y direction. We got two competitors. We get one upward, and we have one that's downward. And again, what is the actual y acceleration that we want? It's 0. So I know that might seem strange. What do we just use g for, the 9.8 meters per second squared? It's not actually doing that, but that's our weird way of getting the gravitational force. That's how much acceleration would cause when acting alone, but it's not acting alone. It's got this other force, completely canceling it, by the way, which means that there is no acceleration. So again, what we get if we solve here is that t2 sine theta has to equal mg. Again, a good free body diagram, you could have said that from the beginning. This is going to have to equal this if they're going to cancel. All right, so what do? Let's go ahead and solve it. We can solve here for t1 and t2. Now, if you look at this equation, you might say, what do you mean? We can't solve for that. There are two unknowns in that equation. Well, this is where you have to be organized, because often at times it can seem like you're at a dead end. But remember, I wrote down both things simultaneously because that gives me two equations. Two equations can be used to solve for two unknowns. So we're good to go here. Okay? We want to know the tensions, but we know the theta that was given. And over here, again, we want to know the tension. We know theta, m, and g. The easiest place to start here will probably be this, because one of the unknowns will pop out directly from here. So T2 is going to be mg over sine theta. And you can certainly work that out to a number, 19.6 newtons, if you want to. And then, of course, that can go straight over into the other one, right? T2, plug in here. If we know that, we can get T1, right? So we're going to be able to do this, no problem. T1 equals, and let me just for kicks put in the symbolic solution. So it looks like this. You might say, why do we plug in the number? I'll talk about that in just a second. You can abbreviate cosine over sine. What's cosine over sine called? Cotangent. Or I guess you could say tangent in the denominator. Doesn't matter. Same thing. In any case, if you plug in the numbers, you get 17. So we have just solved the problem. Have gotten how much tension must be in each rope in order for this sine to be supported in this way. So of course you check your manual, make sure that the two ropes you used can support that amount of tension, or otherwise you're not going to be able to hold up this sine. So, since this is our very first problem, we should probably double check that the answers make sense. I have claimed that these tensions and no other tensions will do to hold up the sine in this way, hold up this sine in this way. It seems like you should be able to have some other values. Well, let me show you why you can't. We have a sine that's 1 kilogram, and it's at 9.8, if we multiply it by 9.8 meters per second squared, we get that the downward force is 9.8 newtons. That's how much gravity pulls on it. So if we want to hold it up, there is only one value for the upward force, right? 9.8 newtons. So this must be 9.8 newtons. There is no other choice. T2 sine theta has to be 9.8 newtons. Well, if you take T2, 19.6 newtons, times sine of 30, that's what you get. Now, you might say, well, why does this need to be so big? Why does this need to be 19.6 newtons when it only needs to hold up 9.8? Well, the reason is because, of course, T2 has several different things going on. This force, 19.6 newtons, part of it goes to the side and has nothing to do with holding up the weight. So part of this force is going to the waist to the side. Only part of it, a fraction of it, will be upward. So if you want the upward component to cancel off gravity, the force as a whole is going to need to be much larger, right? You need just a small, a fraction of it to be 9.8 to support gravity. In fact, it turns out if you have a 19.6 Newton force, like at this angle, the vertical component is 9.8 newtons, but you also occur 17 newtons to the side. 19.6 times cosine of 30 is 17. So how much must the other rope pull back? Must pull back 17. If this comes out to be 17 as a whole, then this has to be 17, right? So no other number will do. No other numbers for T1 and T2 will suffice. Because otherwise you're going to have an imbalance in the forces in either the vertical or horizontal directions. And we have that. The premise of this problem is that the mass just stays there. Okay? So there we have it. Let me just give a couple words on this going forward. The first of which is that these numbers are going to increasingly not arrive. Okay? These solutions, I've just boxed them, are called symbolic solutions. So this is symbolic solutions as opposed to numerical solutions. Symbolic solutions are better. You may not used to the answers for a math problem be a bunch of letters, but they are better. Here's why. Those are the expressions that will give you the answer for this problem for any mass and any angle, not just a particular mass and angle. That's a much more powerful statement, right? So these will give you for any variables, any variable values, not just these particular ones. So the analogy that I would give you is, what if someone told you this is your homework problem, but they're going to say, the number delivery truck that's going to give you theta and m is running late, so can you work as much of the problem as possible before I tell you those numbers? And you can get all the way down to what's in these boxes. So then when someone shows up and says, here's the particular m and theta I want you to use, you're done in like 30 seconds. You just put those numbers into your expressions. It's a much more powerful way of solving problems by symbolic solutions. Okay? Now we will increasingly move towards that. So the number delivery truck is not just going to be running late, but at some point, the number delivery truck just doesn't exist. Okay? So the way we will work problems is given variables. So things that are allowed in your answer. So instead of numbers, they're just things that you can consider to be given. Okay? So our variables are going to split off into 3 different categories. So our variables are going to be split off into givens, which we usually have been marking with a check mark. They're going to be letters, though, not numbers. They're going to be what we want. Those are also going to be different letters, but things that we're looking for. And there's also going to be a third category of don't know, don't care, which we've been typically marking with a cross-off. It's the same as the constant acceleration strategy. The only difference is that the things we know won't be numbers, they'll be just letters. Things we want will be symbolic solutions, and the don't know, don't care will be variables that we introduce for the purposes of problem solving that we should not leave in the answer. That's the rules of the game. You can't just make up something and then include it in your answer. Because if you could do that, you could say like, T2, what is it in this problem? Smiley face. What's smiley face? The right answer. Okay? If you can make up your own letters, then it's anarchy. Okay? Now you might say, who would do that? Okay? Well, people do it all the time. Not quite so ridiculously, but they might say like the answer is mg minus theta, mg minus smiley face over sine squared of theta or something. And they're like, yeah, look at that, I solved for it. Well, you included your own variable in there, so you could just say, what is the value for smiley face? It's whatever it would give you the right answer. Okay? So remember, the rules of the game are that you have to get rid of these. So your final answers should be in terms of given variables and known constants like g and stuff like that. Okay? All right. So the final order of business that I want to do here is just tell you what we just did and formalize it into a problem-solving strategy that you can apply to any problem. It's a recipe that you can use to bring order to this stuff so that you don't get lost. Okay? Here is the problem-solving strategy. And I'm going to include a few things that we may not even be able to fully appreciate yet. Problem-solving strategy for forces. But at this point, it's not like the whole thing is going to seem completely alien. Okay? It's a 6-step recipe, and if you try to just do it all free-willy on the homework, it's not going to work, trust me. These problems are too hard to be unorganized. So step 1, you want to ID your object of interest. It's pretty obvious in the problem I just did. It was a sign. But with problems with multiple objects, maybe you should focus on just one. Then you want to identify forces that act on it. So forces that act on that object, not somewhere else on something else. Then you want to choose your axes. So here's what you do. If the direction of the acceleration is known, pick one axis along it. That is incredibly convenient. We'll see that that is what leads us into some weird choices. But if the direction of the acceleration is unknown, or it's 0, then just minimize how many components you're going to have to deal with. That's what I did in my problem, by the way. Okay? I didn't have an acceleration, so why not pick some axes where I have to break up less things into components rather than more? Then, you're basically, at this point, we're well done with the physics. You're breaking up digesting the problem in easier chunks, an x chunk and a y chunk. You want to do f net x is the sum of your x components, is max. F net y, broken up into components, dot, 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 that gives you your y acceleration, and then you solve for 2 unknowns, up to 2 unknowns. That's basically your strategy. Oh, and I guess, I usually number this in 6 steps, I skipped a step. So this is step 5, and this is step 6. And step 4 is just to break into the components before you do that. So that's the strategy we just took, and that's the 6-step plan that you can take for every problem on homework 4, basically, and you'll find that it works. Object of interest, forces, choose some axes to digest, break it into components in that, get your 2 unknowns, the 2 equations, and solve for up to 2 unknowns. So we'll do more problems like this. Mixing in more forces, and we'll do that all next week.